So, as you guys saw in that Veritasium video, light waves do in fact behave kind of like any other waves, whether it be sound waves or water waves for that matter. So let's just take a look at those water waves in a bit more detail. Let's just say that down here we have S1 and S2, two sources of sound waves. So what's going to happen is these two sources are going to be made to vibrate in phase. And when I say that they're going to vibrate in phase, what I really mean is that the crest from each of these sources are going to be created at the same time, and the troughs will be created at the same time as well. Let's just call these dotted lines the troughs, okay? And we'll call these solid lines the crests. And you'll see that the crest from S1 and crest from S2 seem to be created at exactly the same time. The trough over here and the trough over there are also created at exactly the same time. If you look at the diagram, there also seems to be this imaginary line that seems to go right between the midpoint of S1 and S2. So if I take a look at the straight line between S1 and S2 and find the midpoint, that perpendicular line is often going to be referred to as the right bisector. Okay? Now let's just pretend for a second that, I'll just zoom back out. Let's just pretend for a second now that you actually had an imaginary line somewhere over here. Okay, so somewhere over here you had an imaginary line, and let's say that this imaginary line kind of represents a screen. Okay, kind of like you saw in that video. And what I want you to do is I want you to look at every single point where the waves from S1 and S2 meet at the right bisector. So if I take a look at that right bisector again, and if I take a look at every single one of these points, you'll see that in fact, and again maybe I'll just mark this off, if I take a look at this point over here, this point here, this point there, and if I continue all the way along here, you'll notice that in every one of these points you have the crest meeting up with another crest, or a trough meeting up with another trough. So let's just take a look at this in a bit more detail. And what I want you guys to do now is take a look in a bit more take a look at this point over here, and I'll just highlight this in blue. And what I want you to do is I want you to imagine now how many full wavelengths a wave from source number 1 has to travel to get from here to that point. And again, just to remind you guys, what exactly is the definition of a wavelength? Well, you know for a fact that a wavelength is nothing more than a distance from one crest to another crest, or from a trough to another trough. And just as a quick review from last year's grade 11 course, you may recall that if I were to draw a transverse wave like this, you guys all know for a fact that these guys over here are your crests, this over here would be your trough, and you may recall that the distance from one crest to another crest is also the same thing as a wavelength, and that happens to be the exact same distance from one trough to another trough, which would make that a wavelength as well. Okay, so let's go back to this diagram and let's just count the number of wavelengths from source number 1 to that point, and I'll just use my highlighter to see if I can make that point clear. So ready, let's do a quick count. So from S1 I can go from here to the next crest, which would be 1 wavelength, 2 wavelengths, 3, 4, 5, 6, 7, and 8 wavelengths. So as you can see, from source number 1 to this point, the wave travels, the source of the waves will travel 8 full wavelengths. But what about from source number 2? Just because you can see the symmetry here, we can see that from source number 2 it also travels 1, 2, 3, 4, 5, 6, 7, and 8 wavelengths as well. So clearly from source number 1 or from source number 2, the path that the wave actually takes is identical. So really there is no path difference. But here's something else that you might find interesting. If you take a look, are those the only points right along this line where you see crest meeting up with another crest, or trough meeting up with another trough? Well, most of you can see that it isn't. If you look carefully, and again I'll show you this on the left side, it happens over here, 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 and everywhere along this line as well. And in fact, you see the same thing over on the right side. And again, once again, you can see the symmetry of this pattern. So what we're going to say now is that every single point along this line or that line, you also get crest meeting up with another crest, or trough meeting another trough. You may remember from last year's grade 11 course that when this happened, we say that you have constructive interference happening. If this were those water waves, this would be where those water waves would be a little bit greater in amplitude. Okay? If we're talking about sound waves, this is where the loudness or the amplitude of the sound might be loudest as well. If we're now talking about light waves, this is where the light appears to be the most brightest. Now, let's just take one of these points, for example, and I'll take, oops, where's my blue? There it is. I'll take this point over here. We're going to do the same analysis as we did before. I'm just going to do a quick count from source number 1 to that point. And you'll notice that if I do this, there should be about 7 wavelengths. Let's do a quick count. So I got 1, 2, 3, 4, 5, 6, 7 full wavelengths. If I do the same analysis from source number 2, I think most of you can see that it will be in fact 8 wavelengths. So let's do that again to confirm. 1, 2, 3, 4, 5, 6, 7, and in fact you do see 8 full wavelengths. And again, you'll notice that if I did the exact same thing for all the other points, there seems to be a difference of a full integer of a number of wavelengths. So what I've done here is I've taken the liberty of drawing in for you guys this row of areas of constructive interference, as well as this row of another area of constructive interference. And you'll kind of notice that the distance between the central row, or the 0th row if you will, to the first row, to the second row, to the third row, these distances seem to be equidistant. Equidistant, and you'll notice that the same thing occurs on the right side as well. But for now, let's just focus on the left side and take a look at those ones in a bit more detail. If you take a look at, and again, let me just draw this in here. If you take a look at this point in particular, I think most of you can agree that this point is also going to be 8 wavelengths away from source number 2, but only 6 wavelengths away from source number 1. 1, 2, 3, 4, 5, and 6. And if you take a look, if it travels 6 wavelengths from here and 8 wavelengths from here, I think we can all agree that the source of the waves from source number 2 travels a bit further. How much further does it travel? It actually travels 2 full wavelengths further. And of course, from S1 and S2, if you take a look at those points to this last point, I'll just shade it in blue, you can see that it must now be 3 wavelengths apart. Okay, so now that we've taken a look at all of the areas of constructive interference, let's take a look at all the areas in between. So what I want you to focus on now are, and again, let me just play around with this a little bit. I want you to focus on these areas. Okay, so this is, if you take a look carefully, you'll notice that from source number 1, you have, well, let's say, for example, this point over here, you have a trough, but from source number 2, you have a crest. And as we said before, whenever a crest and a trough meet, what you're going to end up with is a canceling of waves, or an area of destructive interference. And this seems to happen in a couple of places, and they all happen to be, once again, equidistant. So here's another area of destructive interference, and yet another one, and so on and so forth. So what's happening in this case is that if we do another analysis of how far the waves travel from source 1 and source 2, they can't be 1 full wavelength apart. Now they must be half a wavelength apart. So just to confirm, let's take a look at how far the wave travels from source number 1. So from source number 1, it would now travel 1, 2, 3, 4, 5, 6, 7 and a half wavelengths. How far is it from source number 2? Well, it should still be 8 wavelengths. 1, 2, 3, 4, 5, 6, 7, and 8 wavelengths. So clearly, this point right there, or any one of these points, is going to be different by about a half a wavelength. If you do another analysis for this row of destructive interference, you'll notice that the path difference would be not half a wavelength, but 1.5 wavelengths. If you take a look at the analysis of this row of destructive interference, you'll notice that the path difference taken between S1 and S2 is now going to be 2.5 wavelengths. And this pattern continues on for the total number of, patterns that you see. So what we're going to do now is we're going to come up with better names for all of these points. If you take a look, or not take a look, but if you were to draw a straight line to represent a screen that were to go right across the back here, you would notice that if this were in fact light waves, you would find that all of these points over here would represent areas where there's constructive interference or very bright light. If you take a look at all of these areas, you would see that the light kind of dims away, so it becomes very dim or not so bright. We're going to call all of the bright areas antinodes. So this would be called an antinodal line, another antinodal line, antinode, antinode. All the dark areas would be nodal lines. So this would be a nodal line, and a nodal line. Okay, and this applies again to all forms of waves. And if you take a look at this pattern of, let's say, bright, dim, bright, dim, bright, dim, and so on and so forth, that pattern that you would see on a screen is what we call an interference pattern. Only things that behave as waves show this interference pattern. Like I said, water waves, sound waves, and light waves. Okay, so only these things would show this classic interference pattern. And it turns out that we can come up with a simple equation to talk about the path difference that causes this constructive and destructive interference. One thing I would like to point out, though, is that this pattern can be seen for any type of a wave, and the wave pattern that you see is always going to be identical as long as these three things are always true. The frequency of the two sources are always the same. That means the frequency of the wave at S1 and S2 cannot change. The distance between the two sources remain the same or constant, and that the 2-point sources are always, vibrating in phase. Okay? Now let's turn the page over to the other side. So what we're going to do here is we're going to see if we can draw a straight line between source number 1 and, let's just say, the first nodal point. So if I take these 2 points, what am I doing here? Okay, so source number 1, and I point on the first nodal line. I'm going to take another line and connect it from source number 2 to the exact same point. So let's see if I can make this work out a little bit better. Okay, so that seems to work out okay. And let's just see if I can put a little point right around there again just to make this look good. Now I do promise you this is not another triangulation thing that we're going to talk about. It's strictly just the path difference that we're looking at. So let's take a look at that path difference. So if I were to talk about the path difference between S1 and point P, maybe I should label this as point P, what I would find is that the distance between, or the difference between point 1 source 1 and point 1 source 2, or the absolute value difference between these two guys, would actually be 1/2 of a wavelength. So 1/2 lambda. If I were to do the exact same thing from, let's say, source 1 to, let's say, the second nodal point. So where exactly is the second nodal point? Well, let's just choose this to be our second nodal point, and I'm just going to choose that randomly. I would notice that the distance between point 1 S1 and point 1 S2 to be not half of a wavelength, but 1.5 wavelengths instead. So let me just write that down. So from point number 2, which is the point on the second nodal line, S1 minus 0.2 S2, that would be equal to, like I said, 1.5, or if you wanted to write that as a fraction, 3/2 lambda. And you could say the exact same thing for the distance between any nodal point S1 minus any nodal point S2 to be equal to, as a generalization, n minus 1/2 lambda. So if you take a look at the right side of this equation, you might say, well, where did this n minus a half come from? What does it mean? When I talk about n, n basically represents, let me just write this down, where n represents the nodal line, if you will. Okay, so is the point on the first nodal line, second nodal line, third nodal line, etc. And as you know, the first nodal line is the first nodal line away from that right bisector. The second nodal line is a point on this second nodal line away from the right bisector, and so on and so forth. And if I wanted to make a generalization for any antinodal line, so that would be a point where you would see bright patterns, we could say the exact same thing, but this time the path difference would be not n minus a half lambda, but just n lambda. Okay, so one thing I want you to take a look at is for both of these equations, on the left side you have Pn(S1) minus Pn(S2). Same thing down here. That part of the equation is what we're going to refer to as the path difference. So this part over here is what we're going to label to be, where is it there? What we're going to label to be the path difference. Okay, and I'll leave it at that for now, and hopefully I will see you guys at noon later on this afternoon. Okay, thank you.